Good morning, all of you. Yesterday, we discussed about relation between surface energy and surface tension. Surface energy and surface tension. Okay. So for that, I have taken this model. So rectangular frame. Rectangular frame connected with there is a freely moving wire, so that it will form a closed loop. So based on that, we have done work against the surface tension force. Work done against the surface tension force is we have written here delta W, or you can say W is equal to T. Actually, surface tension force is equal to, in this case, T into 2L with respect to freely moving wire of length L. Okay, then delta W work done is equal to force into displacement. So your force is T into 2L. That means applied force is equal to surface tension force. With that force, you can trying to do the work. So that T into 2 into 2L into displacement is, let us say, X here. So that force into displacement. So that T into 2L into X. So that will give 2L into X will give delta A. That means increase in area. Okay. So why 2 times of Lx I taken? Actually, A means L into X. That means there is two areas. That means two surfaces you can consider, top surface and bottom surface. For this soap liquid thin film. So that because of the two areas, 2 into Lx is equal to written delta A. So that delta W is equal to T delta A. So this delta W is you can take it as the surface energy. Sorry, delta W is the work done, and work done per unit area, delta W by delta A, we can take it as the surface energy. Then, but in this equation, delta W by delta A is equal to T. So that here surface energy is equal to surface tension. That we understood. And dimensional also we checked same. Surface tension, surface energy dimensions are same. M L0 T minus 2, M L0 T minus 2. Okay. So after this we understood. Then finally we have taken this equation delta W is equal to T delta A, or simply the delta W can take W or W dash. W dash is equal to T delta A. What is the W dash? The additional work required, okay, to increase the surface area. Okay. So that is the point you have to understand. Next, work done to form a liquid drop we see. So liquid drop initially with the small drops it is forming a big drop of radius capital R. Then final area, that bigger drop area 4 pi capital R square. Now work done is equal to work done to form this drop is T into delta A. Okay. So that T into delta A means 4 pi R square T into A2 minus A1. Delta A means final area minus initial area. So T into A2, what you can say? 4 pi R square, final area. Minus initially, we can't say any area, just it is forming. So 0. So that work done is T into 4 pi R square. That we have done. Next, work done to increase the radius from R1 to R2. So W is equal to T into A2 minus A1. That is T delta N. So T into A2 is 4 pi R2 square, final area. A1 is 4 pi R1 square. So that 4T into 4 pi R2 square minus 4 pi R1 square. So this is 4 pi T into R2 square minus R1 square. Next we have done work done to increase the radius. That means R1 is R, R2 is NR. Then you can substitute. NR whole square is N square R square minus R square. That is 4 pi R square T into N square minus 1. Up to this we discussed. Are you clear up to this? Yesterday evening class we discussed this. Next case we will go fourth case. Are you able to follow, my dear students? Yes?
Yes, sir.
Okay, very good. Suppose we can take now work done to increase area A to NA. Area is increased from A times to N times of A. Then what you should do? W is equal to T delta A. The T into delta A means N into A, final area minus initial area A. So this will become T into A into N minus 1. Work done to increase the area A into N times of A. So that will be T into A into N minus 1. Are you clear this? Next application will go. Work done to increase. Suppose you can take a initial volume of the drop of liquid is V. Initial volume. Let us say spherical. You can say spherical in terms of volume V. Initial volume V. Then work done to increase the volume. Increase the volume to NV. What is the work done to increase the volume? N times of V. Okay, for a spherical droplet. For that first, what you can write work done? Work done W is equal to. Here a spherical drop of water, right? A liquid drop I said. Liquid drop. Work done to increase the volume of the liquid drop from V to N times of V. Then here work done we know already. Work done formula T delta A. But we need to discuss about this volume. So normally, suppose 0 to A area, you can take what is the formula I said. Suppose 0 initially, finally A. A means 4 pi R square. Then A minus 0, initial area 0 to final area A. Then T into 4 pi R square. This is the work done initially, 0 to A. That means your work done directly proportional to R square. Radius of the square of the radius. Suppose initial volume work done to form a V volume drop, you can imagine W. Work done to form initial volume V is W. Then to increase the volume N times of V, then what is the additional work is required? You can imagine like this. Work done to form a V volume of drop is W. Then work done to increase from V volume to NV volume, N times of V. It is 10 times of V, you can take 100 times of V. Then what is the work done? Further simply you can imagine. First you can take volume V is equal to 4/3 pi R cube. 4/3 pi R cube. Then now new volume V dash is equal to NV. That is 4/3 N times of 4/3 pi N times of 4/3 pi R cube. This is the new value you can imagine. Now you can interpret in terms of work done directly. See here, the relation between V and R you can see first V proportional to R cube. V proportional to R cube. N you can keep aside. V proportional to R cube. Okay, then V is equal to some C R cube, some constant. Or just proportionally you can establish. V proportional to R cube means V power 1 by 3 proportional to R. V power 1 by 3 proportional to R. Then V power 2 by 3 proportional to R square. V power 2 by 3 proportional to R square. Then I want W proportional to R square. That means W proportional to V power 2 by 3. In terms of volume directly I take it. W proportional to V power 2 by 3. Are you clear this step? W proportional to V power 2 by 3. Yes or no? For N times of volume, then W dash proportional to NV power 2 by 3. That means W dash proportional to N power 2 by 3 into V power 2 by 3. W dash proportional to N power 2 by 3 minus into V power 2 by 3. Next, now additional work we are talking. Already W work is done to form a V amount of volume of liquid. Then additional work is W dash minus W. W dash minus W. That means N power 2 by 3 into V power 2 by 3 minus V power 2 by 3. Actually, here proportionality constant will keep some constant C. Here also will keep constant C. That constant C you can write here. Okay. So that what is the value? C into V power 2 by 3 into n power 2 by 3 minus 1. N power 2 by 3 minus 1. The C into V power 2 by 3, what you can write? W. Here, this is W. Then W dash minus W is equal to W into n power 2 by 3 minus 1. This W dash minus W is additional work. Additional work required to increase the volume from V to n times of V. That is initial work into n power 2 by 3 minus 1. Are you clear this? Yes or no? Additional work required to increase the volume from V to n times of V. My dear students, are you able to following this concept? Yes or no?
Yes,
Please
sir.
tell me. Yes, very good. Suppose a simple understanding. A liquid is taken from a, this is also interesting concept. A liquid is taken from a square container. A liquid is taken from a square shaped container. Square shaped container like this. Square shape. A cubic inside the surface is like a square into a cylindrical type container. Surface is like a circle. Surface is like a circle. So liquid is taken from here to here. Okay, then in that case, what is the work done? Additional work required in this case. So that depends on the surface area only. Here, what is the surface area? Suppose square side is A. Then area, initial area, A1 is A square. So this area of the surface, suppose the radius is R. Then this area A2 is pi R square. Okay. Then you can say work done W is equal to T delta A. T delta A. That is T is the surface tension. T into delta A. A2 minus A1. That is T into A2 minus A1 pi R square minus A square. Okay. That means the additional work required to change in the surface area. To change the surface area. Okay. So this is about additional model. Are you clear this? Next we will go for one more interesting topic. Work done to required. Work done required. Work required. To split a bigger droplet of water. To split a big drop of water into smaller drops. Into small drops. Into smaller droplets. Okay. Suppose you can take a bigger droplet and it's a smaller droplet. Let us say this is the bigger droplet of water. This bigger droplet, let us say radius capillary, and is forming a smaller drops. The smaller drops, let us say n drops. Each radius is smaller. Then what is the work required to split bigger droplets of water into smaller droplets? Are you clear this? So here, what is happening? Surface area increasing or decreasing? Means surface area increasing. Surface area will be increases. Surface area increases. This is the point you have to understand. Now, what is the initial volume? In terms of conservation of volume, you can say initial volume is 4/3 pi r cube. volume will be constant, volume of the drops. Final volume n times of, by conservation of volume or conservation of mass, you can take n times of 4/3 pi small r cube. Or replay this step by conservation of volume, 4/3 pi 4/3 pi cancel. Then capital R cube is equal to small n into small r cube. Then capital R is equal to cube root, you can take both sides, small n power 1 by 3 into small r. I declare this capital R is equal to small n power 1 by 3 into small r. Right. Now, so let us say initial area A1, you can imagine, final area A2. Then work done against the surface tension, W is equal to, let us say T is the surface tension of the liquid or water, T delta A. T delta A, you can write T times of delta A, A2 minus A1. Okay, then this work done W is equal to T times of A2. What is the A2? Final surface area. Final surface area means n number of droplets, n into each drop surface area, 4 pi small r square. 4 pi small r square, that is the final surface area. Minus initial surface area, 4 pi capital R square. 4 pi capital R square. Okay, so this equation you can write in terms of small r or in terms of capital R. Suppose you can write in terms of small r, you have a relation, you can see capital R is equal to n power 1 by 3 into small r. Okay, then you can write capital R square is equal to n power 2 by 3 into small r square. Okay, suppose if it is small r square is equal to n power minus 2 by 3 into capital R square. Okay, they like this, any form you can take. Now it's a T into 4 pi common, 4 pi T into n. In terms of small r square, you can write small r square minus capital R square. Capital R square, what you can write n power 2 by 3 into small r square. Okay, so then small r square you can take common, 4 pi T into small r square. Answer is n minus n power 2 by 3. N minus n power 2 by 3. This is the additional work required to split the larger droplet of water into its smaller droplets. I require this, all of you. Yes or no? Four pi T small r square into n minus n power 2 by 3. Same thing you can write in terms of capital R also. In terms of capital R, what you can write? From this equation you can write W is equal to T into 4 pi into 4 pi common n into small r square. Small r square, what you can write? N power minus 2 by 3 into capital R square. N power minus 2 by 3 into capital R square minus capital R square. Then now you can write this is 4 pi T into capital R square, you can write 4 pi capital R square into T, n power 1 into n power minus 2 by 3, that is n power 1 minus 2 by 3, that is 3 minus 2, n power 1 by 3, n power 1 by 3 minus 1. This is in terms of capital R square. I declare this 4 pi T R square into n power 1 by 3 minus 1. Are you able to following?
Yes, sir.
Right. Now this also you can write in terms of volume of drop also. Suppose we know volume of drop is V is equal to 4/3 pi r cube. 4/3 capital R cube. 4/3 pi capital R cube. Now You can write in terms of 4 pi r, that 4 pi r square I can write in terms of volume. That means 3 multiply 3 v is equal to 4 pi r cube. That means 3v by r is equal to what you can write 4 pi r square. 3v by r you can write as 4 pi r square. Then you can substitute here. Then from the above equation you can write w is equal to w is equal to T into 4 pi r square means 3 volume, 3 times of V, 3V by R into n power 1 by 3 minus 1. This R you can take inside, then you can write 3VT into n power 1 by 3, n power 1 by 3 by R minus 1 by R. Okay, but you can see the previous equation. See here, R is equal to n power 1 by 3 into small r. Then what you can write from this equation? 1 by small r is equal to, you can write as n power 1 by 3 into capital R. 1 by n power 1 by 3 divided by capital R. You can write like this. R is equal to n power 1 by 3 into small r. Then 1 by small r you can take the left side. Then 1 by r is equal to n power 1 by 3 divided by capital R. That means n power 1 by 3 divided by capital R is equal to 1 by small r. Then this you can substitute as 1 by small r. That means you can write as 3Vt into 1 by small r minus 1 by capital R. This in terms of two radius, smaller drop radius and bigger drop radius. 3Vt into 1 by small r minus 1 by capital R. Are you clear this equation? In terms of volume, we found V is the volume, T is the surface tension, not temperature. Are you clear this?
Yes, sir.
Right. So this is about splitting of a bigger drop into smaller drops. So in the splitting process, the process will be two types, isothermal and adiabatic. You know, thermodynamics already running parallelly. So isothermally, what happened? Adiabatic, what happened? If it is happen isothermally, what is the meaning of isothermal? Constant temperature. If the splitting process happen isothermally, at constant temperature, then first of all energy either released or absorbed. So here from bigger drop to smaller drops, area increased. Area increased. Area increased means final area minus initial area. So work is done to increase the area on the bigger drop. That means work done by external process, by means of external energy, work is done on the bigger drop to divide into smaller drops. Then there is a surface energy increases. Surface energy increases. So that means if the splitting process occurs isothermally, temperature is constant, no doubt. If the splitting process happen adiabatically. Okay, next adiabatically means constant heat Q. Adiabatic. Adiabatically. If the splitting process happen isothermally, temperature should be constant. The conversion of energy, whatever it may have, in another form happen, conversion of energy. Temperature will be maintained constant. But in adiabatical process, that the drop uses internal energy. The splitting process, actually it is taken suppose only the energy of bigger drop only. So surface energy increases. Then some other form of energy should be decreases now. Because of area increases means surface energy increases. Okay, that means the drop uses internal energy so that the temperature decreases. temperature decreases. That means the smaller drops having low temperature. Smaller drops having low temperature. That means the droplets will be cooled down. That means if you split the bigger drop into small drops, the droplets will become slightly cooled down if it is done adiabatically. Okay, are you clear this point? Similarly, you can take a combining process also. That means small droplets combine into bigger drop. So that you can do. I'll give you a work for you. So how, same mechanism. Okay. So in that case, you have to calculate work done or required to combine smaller drops into bigger droplets. Okay. Right. Next we'll go for bubble. Up to now we have discussed about droplets. Now bubbles. Bubble means what? Suppose you can take a soap bubble. Soap bubbles. So what is the difference between bubble and a droplet of water? Bubble and a droplet of water. Anybody can say the difference? Is the droplet, D for droplet, B for bubble. This is the B for bubble, D for droplet. So this a droplet is either water or any other liquid, only one surface. Droplet is only one surface. That is outer surface. Are you clear this point? Droplet only one surface, that is the outer surface. Whereas the bubble having two surfaces. Inner surface and outer surface. So that means if it is two surfaces having certain small thickness. Okay. So that it has two surface areas actually. It has two surface areas, inner surface and outer surface. Then what is the total surface area you can say? Suppose this radius is R, this radius also R. Here this surface area is simply 4 pi R square. This surface area is simply 4 pi R square. But this surface area 2 times of 4 pi R square. Keep in mind. 2 times of 4 pi R square for bubble. Then what is the surface area for bubble? It is 8 pi R square. It is 8 pi R square. Are you clear this point? Difference between soap bubble and liquid drop of water? Yes or no? Yes. So now suppose work done to blow a soap bubble. Work done to blow a soap bubble from initially 0 surface to R surface area of radius R. Then what you can take T is equal to, W is equal to T times of A2 minus A1. For soap bubble I am talking. Initial area 0, final area A2. Okay, to blow a soap bubble. Then D times of, what is A2? Final surface area, 8 pi R square. Initial surface area starts from 0, you can imagine, minus 0. Now, what is the work done to blow a soap bubble from initial 0 to final radius R? 8 pi T R square. Are you clear this? Answer is 8 pi T R square. Or 8 pi R square into T. Are you clear this? For soap bubble. Then liquid drop. Liquid drop is 4 pi R square into T. W is equal to T into final area 4 pi R square. Initial area you can take, imagine 0. Then T into 4 pi R square minus 0. That is T into 4 pi R square. So this is the difference between liquid drop and soap bubble. You have to remember. Liquid drop and soap bubble. So in the soap bubble case, everywhere you should take as 2 times. Everywhere you should take as the 2 times of surface area. Inner surface area by considering inner surface area and outer surface area. Okay, compared to liquid drop. Right. Now I'll say a few more applications. Suppose a V volume of the liquid drop. So suppose again I have taken liquid drop. In that case, initial volume is V. Now split into smaller drops. So in the case of what happened, the internal energy utilized as, so to convert into smaller drops. As internal energy decreases and then surface energy increases. Suppose if the smaller drops are combining into bigger drop, the smaller drops are combining into bigger drop, what happened? Smaller drops are combining into bigger drop. Here surface area decreases, then internal energy increases. Okay. So that means the temperature will be rises. Temperature will be rises. Suppose if it is happen at isothermal at constant temperature, then increase in energy, it will be converted to some other form. Let us say bigger drop will be moving with some speed v. Bigger drop will be moving with certain speed v. That means increase in energy will be converting into kinetic energy. The increasing energy converting into kinetic energy, then what is the final velocity of the bigger drop after combining? What is the final velocity of the bigger drop after combining? Okay. So you can imagine work done. How much work is required? W we know already. 3 VT into 1 by small r minus 1 by capital R. 1 by small r minus 1 by capital R. So this is the minimum work required. Where V is the volume, T is the surface tension. Now what is the kinetic energy? K is equal to half mv square. This V is speed of mv square. So this work is done by utilizing the surface energy. That means decreasing the surface energy. Now this energy, here this happen at constant temperature. So let us say theta temperature constant. Then that loss in surface energy will be utilizing in the form of kinetic energy, gain in kinetic energy. That means this work is equal to kinetic energy. Are you clear this step? At constant temperature it is happen, then the temperature will not rise, then the droplet will move certain speed. So now you can equate 3 VT, V is the volume, T is the surface tension, into 1 by small r minus 1 by capital R. Minus 1 by capital R is equal to half mv square. Of m square. Okay. Here m mass of the droplet you can write as m is equal to density into volume, rho into v. You can substitute this half rho into v, density into volume, into v, speed square, is equal to 3 VT into 1 by small r minus 1 by capital R. Okay. Now this volume cancel each other. Then finally you can find the speed in terms of these values. V square is equal to this 2 times of 3, 6 t by rho will come this side, 6t by rho into 1 by small r minus 1 by capital R. Are you clear this? Then V value, final speed, V is equal to root of 6t by rho, where T is the surface tension, rho is the density of liquid, into 1 by small r minus 1 by capital R. This is about the final velocity of the droplet of liquid after combining into single drop. This entire process happening isothermally. Then loss in surface energy will be converting into gain in kinetic energy, so that the velocity will be increases from 0 to v. So that is equal to root of 6t by rho into 1 by small r minus 1 by capital R. Are you clear this step? This equation? Yes, very good. So same process, suppose if it is happen, this is happen, I said isothermally. Suppose if it is happen adiabatically, the same process will be happen adiabatically. What you can expect? The same process happen adiabatically. Adiabatically means what happen? The temperature either loss or rise. So in this case, what I said, all the smaller drops combine into bigger drop. That means surface area decreases. So that surface energy will be converting into here heat energy. So that you can expect a temperature rises. So this whatever work is done, work done by the drops, that is you can take instead of kinetic energy, you can take heat energy. Okay. So then by using Joule Thomson heater, W is equal to what you can write? JQ, heat energy. W is equal to JQ, where J is the equivalent of heat, joules, JQ, where Q is equal to ms delta T. Q is equal to ms delta theta, rise in temperature. So from this you can calculate rise in temperature. How to do? W is equal to J into ms delta theta is there now, where S is the specific capacity of droplet. So this J ms delta theta should be equal to 3 Vt into 1 by r minus 1 by capital R.